So let's talk about the basis of a vector space. Basis of a vector space is nothing but a subset, say S, with say n elements. If we are interested in finding the basis of our n-dimensional vector space, then the basis will have n elements. Say these are the elements. So basis is nothing but a subset of V, Vn basically, and it satisfies these two properties. One is that this collection, this S, okay, this S is a linearly independent subset of vectors, and another condition is there that S generates or whole vector space, right? So it's a subset, okay? Basis is a subset of our vector space. It contains elements, some elements. You can say that if the dimension of the vector space is n, then the number of elements that will be present in our subset will also be n, okay? But it is it is necessary, but sometimes there can be a situation when we don't know the dimension of our vector space, okay? So in that scenario we can say that it is a subset, and it is a subset of vector space, and it satisfies the following two properties, two conditions. So first condition is that S, the vectors that are present in S are linearly independent, and our vector S generates the whole Vn. What do we mean by this statement? S generates our vector space. This statement here means that if we take any vector for all vector V from our vector space, say Vn, and let's suppose that S is having some elements S1, S2, Sn, okay, then this vector V can be written as alpha 1 S1 plus alpha 2 S2 plus alpha n Sn. This is nothing but a linear combination of the elements of our basis. So each and every vector of our vector space should be described as the linear combination of the elements that are present in our basis, okay? If all the elements of vector space can be represented as a linear combination of the elements of the basis or elements of the subset that we are going to prove a basis, then this particular set S can be regarded as a basis of our vector space Vn or our vector space V. The first condition is also very important, that this elements of this particular subset should be linearly independent. Then second condition says that each and every element or vector of our vector space should be defined as a linear combination of the elements of the subset, okay, subset S. And if these two conditions are satisfied, then we can say that S is a basis, okay? And the number of elements in set S, or in other words you can say the cardinality of set S is known as dimension of vector space. So the number of elements that are present in the basis is the dimension of vector space. That is why I was saying that if n is the dimension of the vector space, then S will automatically have n elements. But there can be a situation where we don't know the dimension. Then what we'll say, we'll just say that let's suppose that S is the basis and S has some elements like k elements, and we'll try to show that every vector V can be written as linear combination of these k elements. If we are able to show that each and every vector of our vector space can be written as linear combination of these k vectors, then we'll say that our basis contains k vectors, hence the dimension of the vector space will be k. Right? I hope you got a little bit idea. Maybe if you feel that the explanation is fuzzy, please just give me a feedback so that I can make it more clear for you, and it will be helpful for me also. Let's take an example. Say V3 R is our vector space. And we have a subset of V3 as S is equals to 1 0 0 0 1 0 0 0 1. Right. So this is the subset we have of this particular V3 three-dimensional vector space. We can see that if we take any general element, let's say for all V belonging to V3, we can write V as x, y, and z, where x, y, z belong to R, right? So you can see that this V can be written as x into plus y into 0 1 plus z into 0 0 1. Okay, so what are we looking at? You can see it is nothing but x and the first element of S1 or S subset S plus y the second element plus z the third element, right? And all y and z belongs to a real number. So this is the field layer. Okay, so you can see that this is the linear combination. This particular general vector can be written as a linear combination of the elements that are present in our vector S. So we can say that this S, and in the second condition for this to become, for this particular vector S to become basis is satisfied. What about the first condition? What is the first condition? S should be linearly independent subset of vectors. So you can see here all these three vectors are linearly independent. You can check it. You can check that these three vectors are linearly independent. And we already know about the methods to check whether a particular set is linearly independent or not. Okay, so and such kind of basically basis is also known as standard basis, where we have the collection such that the form is represented by an identity matrix. Okay, like we have these vectors, and if we arrange these vectors as column of the matrix, then we will form an identity matrix like this. So this is nothing but a standard basis. Okay, so if you want to find out the standard basis of 4-dimensional vector space over field R, then you can just write standard basis. It is also known as natural basis. Okay, and the standard basis will be 1 followed by 3 zeros, 0, then 1, then 2 zeros, then 0, 0, 1, 0, 0, 0, 0, and then 1. Okay, again you can see that we can write it like this. This is nothing but I4, right? So we have seen that these are the this is the standard basis, and we have seen the definition of basis, and let's in the next video we'll see some examples and what are the types of questions that are asked in the examples. Okay, thank you for watching. Subscribe to this channel. Bye.